This is a concept that very few people are able to truly explain: driveshaft phasing. It's sometimes called timing, clocking, or U-joint alignment. When it comes to RC crawlers, you'll hear some people say that correct alignment is absolutely critical, and others say it doesn't really matter. So we're going to explore the science behind this concept, and it's entirely possible that both lines of thinking are correct. On this channel, we look at the science behind our grown-up toys. If you're driving a vehicle with a chassis or skid-mounted motor, then there are usually two drive shafts, one to the front axle, one to the rear axle, with twin U-joints, one at each end, probably with a sliding element in the middle that connects the transmission to the axles to drive the wheels. Also, if you're running an MOA, motor on axle, this also applies because you have a single U-joint at the steering knuckle. The theory is that on a typical drive shaft with U-joints on either end, you have to line up the U-joints in a particular orientation. The reason is that if you rotate one end of the U-joint at a constant rotational speed or constant angular velocity, that output coming from the other side of that U-joint is not constant. And somehow lining up two U-joints correctly fixes that irregular, non-uniform rotation. So I fished around some of the popular online crawler hangouts, and people throw around the word phasing and vibration, but I didn't encounter anyone who could really explain why U-joints need to be aligned. So then I turned to some U-joint manufacturers, and surprisingly, even professionals never offered a good explanation why. One piece of evidence to support this non-uniform rotational speed is the very existence of CV joints. CV stands for constant velocity. Why would it be called a constant velocity joint unless the U-joint that replaced it was not constant velocity? You'd probably pick a different name if the constant velocity portion wasn't a novel feature. To me, this is simply not at all intuitive. If you look at a U-joint, it's totally symmetrical left and right. So why would the output suddenly become irregular or no longer constant? It just doesn't make sense to my brain. In fact, one of the earliest publications about U-joints in 1664 by German scientist Gaspar Schott, he also believed that it was a constant velocity mechanism. It was just a few years later that English physicist Robert Hooke demonstrated definitively that the output speed is in fact non-uniform, and the underlying math was eventually worked out. It wasn't until I found this video that it finally clicked in my head.
When an operating angle is created at the front end of the drive shaft, the output of the U-joint no longer travels in a perfect circle.
It kind of reminds me of a secret government military experiment from the 50s, but now I think I get it and I will try to explain it. The governing math equations are quite complicated, and this time I don't think I can recreate these, but there are a couple of easier ways to demonstrate it. Let's take a quick look at what goes into the construction of a U-joint. This is probably the most basic and inexpensive U-joint in the world. And these are actually my Legos from the 70s that I still have. The U-joint is basically three parts. You've got a clevis and this middle piece, which is called the spider, although I've never seen a four-legged spider, or the cross or the journal cross. Then a second clevis on the other side. A clevis is just this C-shaped structure with an axle through it. And there's another clevis coming in this direction, and there are two axles that intersect right in the middle of this spider. On RC-sized U-joints, you usually see a big pin and a small pin. And the reason why that's common is because this smaller pin is pressed through the bigger pin, and that's what holds them both together. On scale RC, this is just a hardened steel pin rotating in a hardened steel outer body. On full-size vehicles, these have needle bearings at each of these four pivots so that they wear a long time and so that they spin smoothly, especially at high speeds. Now, the thing that has always confused me is these are perfectly symmetrical. You've got a C shape here, you've got a C shape here, and this spider cross in the middle. And they're perfectly symmetrical, left to right. It really doesn't make sense to me how spinning the input side at a constant velocity translates into an irregular, non-uniform revolutionary speed on this end. It seems like it should be perfectly matched one-to-one in and out. We're going to find out if there is something going on at this juncture that causes this end to rotate in a non-uniform manner. I started by building a working computer 3D CAD model. This should give us some insight. So I built this 3D model of a universal joint, and it's fully functional, and it should show us exactly how the math works. I can set it to any angle that I want. This is 60 degrees. And it's fully functional. Now, what we're going to observe here is when you have a constant input, we're going to rotate this half of the U-joint at a constant velocity, and then we'll observe what happens on the output side. Now, the best way I can explain what's going to happen is this. You've got this transfer plane, for lack of a better word. This plane is the intersection between this cylinder and this cylinder. And the circle that's drawn or projected on this intermediate plane is what drives the torque from one half to the other half. And if we put a high angle on this, let's say 70 degrees, you can start to see that this drive plane takes on an oval shape. The input is a round shape, which denotes constant velocity, but the output has to track along this oval. The output RPMs has to match the input RPM. So 10 RPM in equals 10 RPM out. That can't change. But the rate at which it circumnavigates that RPM can change. So if you look here, every time this makes one perfect revolution, this also makes one revolution, but it has to speed up and then slow down. Speed up, slow down. For the torque to be transferred across this intermediate plane, it has to change velocity to equal the same one-to-one output matching RPMs. Now, let's see if that really shows up. And let's see if this will run. This one here will be the input, and we will drive that with a constant velocity. Okay, so if we look at this here, this is moving at a constant velocity. And this is the input side. Now let's move it to the output side. You should be able to see how this is going slow, then fast, then slow, then fast. This is moving at a much different rotational velocity than this side. See how this one is constant RPM, and this one changes speed. It goes faster, slower, faster, slower. That is exactly why this is not a constant velocity joint. Now let's add on a second U-joint, which would be similar to your drive shafts. You've got a vertical clevis on this side and a vertical clevis on this side. So you can see one of the axles in the same orientation on both ends. This is considered correctly phased, and I'll show you what that does. Again, I'll animate this. So this is the input, and it's moving at a constant rotation. And you can see this intermediate shaft is rotating fast, then slow, fast, then slow. So here you should be able to see this output is moving at a constant angular rotational velocity. This middle shaft is not. Notice how this middle shaft, and remember these two ends are completely connected, so they're moving at the same rate. Remember, this goes fast over the top, then slow at the end, fast, then slow. So you're basically undoing or unwinding that discontinuity by adding a second joint. Let's see what happens if we don't have the axles in phase. Now I'm going to redefine this so that the center axle is not correctly phased. I'm going to change this to this. Okay, now we have a drive shaft that would be considered incorrectly aligned or phased. You've got a vertical axis here, and on the other end it's a horizontal axis. So these clevises are now 90 degrees from each other. Let's see if this will still unwind that irregular rotational velocity. All right, here we go. So let's look at this end. We've got our constant input. We've got our non-constant output. Then we've got this side moving at the exact same rate as this side because they're connected with the drive shaft. But let's look at what this output side is doing now. You should be able to see this is moving really fast, then really slow. Really fast, really slow. So what we did is we actually doubled this irregularity. I'm not sure I can explain exactly why. It doesn't totally make intuitive sense to me why it does this, but by simply changing that alignment, now look how irregular this rotation is. It's super fast and then super slow. Now, you certainly don't want your axle being driven with this jerky, irregular motion. You want the input to your axle to be as smooth as possible. So can you see that difference in phasing? This is correctly phased, 90 degrees. Correctly phased, incorrectly phased. Parallel axles, 90-degree axles. Now I'll put these side by side so you can see the difference. So there you have it. Now let's look at a very simple demonstration that was inspired by that low-res video from before. So I built this Lego demo that is made from the cheapest, most simple U-joints available, but there's no reason why this won't simulate what any other U-joint would do. So this was inspired by that video I showed you earlier. What we're going to do is have a real simple audio representation of what's going on with these. So I got this free deck of cards a couple weeks ago when I went to a Golden State Warriors game at the Chase Center in San Francisco that happened to be on Chinese Lunar New Year. And it was given to everybody that went by Cache Creek Casino. Never been there, but it's kind of funny because here's the Golden State Warriors logo with some Chinese characters and the Lunar New Year celebration deck. So I've got a Rode microphone here. I'm going to put it down next to the gears, and we'll try to isolate that noise from the motor noise. All right, so got the motor going, and I'm just going to hold this playing card. You can hear that's pretty constant. Here it's pretty constant as well. Now let's turn this at 45 degrees. You should be able to hear that pulsing faster, faster, faster. Let's see how much angle this will actually do. So the input is totally constant. Now this is exactly what would happen on your steering knuckle where there's only one U-joint. So right here about 20 degrees, not much difference. 40 degrees, you can really start to hear it. And then it goes crazy when you get to real high steering angles. So now I'll rebuild this with a second U-joint. All right, now we got two U-joints that we can test. Wow, that really got worse. And the reason is I wasn't paying attention and they're not phased correctly. So I'm going to switch this. So now this middle axle has the pin facing up, the pin facing up, and now we'll see if it remains a constant output. So once again, the input. Look at that, it's still constant. As long as the axles, as long as the input and the output remain parallel, it cancels out that non-uniform rotation. Now, if we turn this, we haven't erased that non-uniform rotation. We're getting it purely from this. So you can hear that pulsing. Now, let's assume you've got a newer vehicle that's got a mid-bearing carrier in the rear, and you've got a couple drive shafts, and it's a custom rig that you built yourself. So not everything is factory designed and lined up perfectly. Let's say your rear drive shaft is not parallel. The input is not parallel to the output. You're going to get some of that non-uniform pulsing at your wheels. And if you've got it like this for some reason, which is entirely possible, you've got some pulsing there. Not too bad. But if you've got some real high angles, if you've got a real high angle on one end and a shallow angle on the other, you're going to end up with some of that non-uniform pulsing. So what you want to do, set these as parallel as possible.
So now I'm convinced that universal joints do not transmit torque at a constant rotational velocity, despite being initially counterintuitive. At least to me it was counterintuitive.
So how important is it on an RC crawler? Here's a few things to consider. The main goal of aligning your drive shaft is to eliminate any pulsing and non-uniform rotation coming from the U-joints, which would cause small speed changes when it gets to your wheel. You want the wheels moving as smoothly as possible, not stuttering and scrubbing traction. The secondary goal is to reduce vibration. A full-scale universal joint has needle bearings on each of the 4 pivots. Needle bearings carry a very high load and don't have much play. They're really accurate. RC crawlers simply have a hardened steel pin that runs through a steel hole.
Because there aren't ball bearings in this type of U-joint, you'll see that there's a little bit of play because the clevis is a little bit loose around the pin. Otherwise it wouldn't turn. Hopefully you can see this in the video. There's just the tiniest bit of play. And this pin as well has some play in it. So there's a little bit of backlash, it would be called technically, in this type of design. On a full-size vehicle, you've probably got virtually zero backlash or play within those needle bearings and axles.
Full-scale drive shafts are very carefully balanced rotationally because they are heavy and they spin at high RPMs. RC crawlers have these loose sliding joints and they're not balanced in the slightest. But they work because they don't have a lot of mass and they don't spin that fast.
RC crawlers and some full-size vehicles have a sliding element that makes up for a difference in movement between the axle and the transmission. And the sliding axle has some play in it that maybe you can see. Otherwise it wouldn't slide if it were perfectly tight. And there's also some bending play. And the less overlap you have, the more bending play there is. You can see there's quite a bit of play.
All of this looseness or backlash in the drivetrain helps to disguise any non-uniform rotation in the U-joints if they are not aligned correctly.
I'm going to hold this wheel totally rigid. And look how much movement there is from one wheel to the other wheel. This is all backlash in the system. This whole drivetrain has been run quite a bit, but I don't think it's much worse than it was when it started. I'd be curious to see what some of your vehicles have. Well, there's this much just in the front axle, and then there's this much in the rear axle. So it seems like a lot of play. I'm not too worried about a small amount of non-uniform rotation with this much play in the system.
Also, if you're building a custom crawler, you want the input and output angles to be parallel and remain parallel throughout the suspension travel as much as possible. If this is not the case, then you won't completely negate the rotational speed non-uniformity. As a general rule, try to keep your drive shafts as straight as possible for smoothness, lower noise, and less friction and wear.
You want to have as shallow an angle as possible on your drive shafts for a number of reasons. You can see that when the axle is dropped to the bottom of the suspension travel, there's quite a bit more angle on the drive shaft. You can see how much angle that adds, and there's really no way around that. You can also see why these axles need a sliding element. Now, one thing that you might consider that wasn't a priority for me on this vehicle is that you want the input shaft and the output shaft to be at the same angle. And as you can see here, my pinion is pointing upwards towards this axle. And at the bottom of the travel, the upper one is fairly horizontal, and this is pointing up towards it. So by no means is the input and the output parallel at the top of the travel or the bottom of the travel. That's not ideal, but it works well enough.
Because an RC crawler is so light, you can get away with a lot of tricks that would not work so well on a full-size vehicle. For example, RC crawlers don't have axle differentials or intermediate differentials at the transmission. Additionally, it's common to have a huge amount of overdrive where the front wheels spin faster than the rear wheels, sometimes as much as 30 or 40%. And there's always a healthy disregard for proper Ackerman steering. All of these things create massive wheel scrub and also help to mask any effects of irregular wheel speed. Finally, take a look at your steering knuckle. It only has one U-joint. The greater the steering angle, the greater this non-uniform rotation becomes. The fast part is faster and the slow part is slower. The sharper you turn, the more unmitigated velocity changes are pulsing at your wheels. This is why full-size vehicles more commonly use CV joints at the steering pivot.
At your steering knuckle, you're going to have a single drive shaft. So you're definitely going to have some non-uniform rotation coming from the drive shaft output into the wheel. The only way around that would be to replace this with a CV joint.
Ultimately, drive shaft phasing probably doesn't matter on a slow-moving crawler. With wheel scrub coming from multiple sources, unbalanced drive shafts, and a loose drivetrain with lots of backlash. But it takes the same effort to time your drive shaft correctly as it does to do it incorrectly. So I recommend doing it right as a matter of principle and discipline. But if you didn't know this before now, and you did it incorrectly, my guess is it wasn't that noticeable or detrimental in any way. And that's why both schools of thought are correct.